In this video we look at the FP1 work on simultaneous equations. Basically we've got to look at simultaneous equations consisting of two equations in two unknowns and simultaneous equations consisting of three equations in three unknowns. And we need to look at how they are linked with associated matrix equations. So let's have a look at the key facts. First of all, we need to realise that any system of simultaneous equations can be written as a matrix system of equations. We need to appreciate that if the determinant of the matrix is not equal to naught, then the system of equations will have a unique solution, and that this unique solution can either be used using inverse matrix methods or by methods such as reduction to echelon form. On the other hand, if the determinant of the matrix is 0, in other words, if the matrix is a singular matrix, then the equations do not have a unique solution. It's possible that the system of equations may have an infinite number of solutions, but it's also possible that the equation will have no solutions at all, in which case the equations are said to be inconsistent. If the determinant of m equals naught, there's no chance of finding an inverse matrix, so to solve such systems of equations we've got to use the reduction to echelon form method. So let's have a look at two examples. The first one is from the June 2010 paper. So the first part of the question says find the values of lambda for which A is singular. A singular matrix is a matrix whose determinant is 0. So we've got to work out the determinant of this matrix A. Now I do this by simply copying down the first two rows of the matrix A underneath the matrix A. And then the evaluation of the determinant is relatively easy. The determinant of A is 3 terms obtained by multiplying together diagonals going from top left to bottom right. Take away 3 terms obtained by multiplying together the terms in the diagonals going from top right to bottom left. So let's see this. So the first diagonal down there is 2 times 2 times 5, which is 20. The second diagonal is 1 times 5 times 3, which is 15. And the third diagonal is 4 times lambda, which is 4 lambda squared. And then taking the diagonals from top right to bottom left, the first one is 3 times 2 times 4, which is 24. The second one is lambda times 5 times 2, which is 10 lambda. And then finally, the third diagonal is 5 times lambda times 1, which is 5 lambda. So there's my expression for the determinant of A, which we can simplify to 4 lambda squared minus 15 lambda plus 11. Now remembering that to say that a matrix is singular is to say its determinant is 0, we're obviously going to be thinking about saying 4 lambda squared minus 15 lambda plus 11 equals 0, so it may well be worth just factorising the expression for the determinant of A as lambda minus 1, 4 lambda minus 11. So the determinant of A equals 0 implies that lambda must be equal to 1 or lambda equals 11 over 4. Moving on to part B of the question. We've been told that lambda is equal to 3 now, so that means that A is the matrix 2, 3, 3, 1, 2, 3, 4, 5, 5. And putting lambda equals 3 into the expression for the determinant of A, we've got the determinant of A is 3 take away 1 times by 4 times 3 take away 11. In other words, the determinant of A is 2 times 1, which is 2. Now we've now got to find the inverse of this matrix A. So we need first of all to find the cofactor matrix. So there's my matrix A, and I've started off with my grid of pluses and minuses. So looking at the first entry, we delete the first column, we delete the first row. The determinant of what is left is 2 times 5, take away 3 times 5, so that is minus 5. In the grid matrix we've got a plus sign there, so the entry is the same as the determinant value. So in this case we've got the entry is minus 5. Moving to the next entry across, so we cross out the second column, we cross out the top row. The determinant of what is left is 1 times 5, take away 3 times 4, which is minus 7. In the grid matrix we have a minus sign, so that means the entry has got to be minus 7, in other words it's 7. Moving on to the third entry, the determinant that we've got is 1 times 5 take away 2 times 4, which is minus 3. The entry in the grid matrix is a plus, so the entry must stay the same as the determinant, which is minus 3. So the entry is going to be minus 3. Moving through now to the first entry in the second row. The determinant of what is left is 3 times 5 take away 3 times 5, which is 0. So the entry is going to be 0. Moving on to the middle entry of our matrix. The determinant of what is left is 2 times 5, take away 3 times 4, which is minus 2. The sign in the grid matrix is a positive, so the entry is going to be the same as the determinant, which is minus 2. Moving on to the right hand entry in the middle row. The determinant of what is left is 2 times 5, take away 3 times 4, which is minus 2. The sign in the grid matrix is a negative, so that means that the entry has got to change sign, so the entry's got to be 2. First entry in the bottom row, the determinant is 3 times 3, take away 3 times 2, which is 3. The sign in the grid is a positive, so the entry is going to be 3. The penultimate entry, the determinant is 2 times 3, take away 3 times 1, which is 3. The sign in the grid matrix is a minus, which means that the entry is going to have to be minus 3. And then finally, we have got the determinant is 2 times 2, take away 3 times 1, which is 1. The entry in the grid matrix is a positive, so the entry stays the same, so the entry is 1. So our cofactor matrix is minus 5, 7, minus 3, 0, minus 2, 2, 3, minus 3, 1. The adjugate matrix is simply the transpose of the cofactor matrix. So the first row of the cofactor matrix becomes the first column of the aggregate matrix. The second row of the cofactor matrix becomes the second column of the aggregate matrix, and the third row of the cofactor matrix becomes the third column of the aggregate matrix. And finally, the inverse matrix is 1 divided by the determinant times by the aggregate matrix. So I've now got my expression for the inverse matrix of A. Finally, we need to solve the system of equations. If we look carefully, we can see that the system of equations can be written in matrix form as A times xyz equals 2 minus 1, 4. If we multiply each side of this equation on the left-hand side by A inverse, then the left-hand side becomes A inverse A, in other words just the identity, times xyz equals A inverse times 2 minus 1, 4. So we've got xyz equals A inverse times 2 minus 1, 4. We know what A inverse is, so we've got xyz must be A inverse times by 2 minus 1, 4. So we've just got to do that little multiplication, matrix multiplication there. And if we perform that matrix multiplication, we're going to get 1/2 of 2, 4 minus 4. In other words, x must be 1/2 of 2, which is 1. Y must be 1/2 of 4, which is 2. And z must be 1/2 of minus 4, which is minus 2. Looking at the mark scheme for this question, for part A there are 2 marks for obtaining your expression for the determinant of the matrix A, and then 2 marks for saying that when the matrix is singular the determinant must equal 0 and calculating the 2 values of lambda. Evaluating the inverse matrix took 4 marks. 1 for finding the determinant of A, 1 for finding the cofactor matrix, 1 for finding the aggregate matrix, and then 1 for the final inverse matrix. And then finally there are 2 marks for using the inverse matrix to solve the system of equations. Let's now move on to a second example, which comes from the January 2011 paper. We have a system of equations. We're told that the equations are consistent. That means the system of equations certainly has some solutions, and we've got to find the general solution of this system of equations. If we write the equations in matrix form, we see that the matrix that we need to be looking at is the matrix 1, 2, 1, 2, 3, 1, 3, 4, 1. If we work out the determinant of this matrix, we'll see that the determinant of this matrix is actually equal to 0, which means that the matrix does not have an inverse. It means that we're in one of these situations where the equations may have lots and lots of solutions, or it may have no solutions at all. When the determinant of a matrix is 0, we've got to use the reduction to echelon form to solve the equations. All of the comments that we've made so far on this question you would not need to make in answering an examination question. The fact they are telling you that these equations are consistent should be suggesting to you that in all likelihood the determinant of the matrix is going to be 0. The fact they haven't asked you to think about the matrices in this question ought to be suggesting a solution by reduction to echelon form. So, here are our three equations. Looking at the three equations, it's going to be very easy to eliminate z from the second and third equations. We can eliminate z from the second equation by simply taking the second equation and subtracting the first equation. So 2x take away x is x, 3y take away 2y is y, z take away z is nothing, 3 take away 1 is 2. Similarly, we can eliminate z from the third equation by subtracting equation 1. 3x take away x is 2x, 4y take away 2y is 2y, z take away z is no z, and lambda take away 1 is lambda minus 1. So we've now got three equations. The first equation we've done absolutely nothing with. The second equation, or the revised second equation, has now only got x and y in it, and the revised third equation has only got x and y in it. Okay, we're now going to try and eliminate y from the final equation, from equation 3. And we can do that relatively easily by taking the third equation and subtracting twice the second equation. So what have we got? We've got 2x take away 2x. Now that is 0x. I am going to write this as 0x because what I was trying to do at this stage was eliminate the y's. So the 2x take away 2x is leaving me with 0x. Looking at the y's, well, the whole point of doing the y's was to eliminate the y's. So I've got 2y take away 2y is 0y. Since I was trying to eliminate the y's, I'm not going to write the 0y down at this stage. And then on the right hand side I've got lambda minus 1 take away 2 times 2 giving me lambda minus 5. So I have now reduced the equations to echelon form. I've got x plus 2y plus z equals 1. That's my equation in 3 unknowns. X plus y equals 2. That's my equation in 2 unknowns. Naught x equals lambda minus 5. That's my equation with only one of the unknowns, x, y and z in it. That final equation, naught x equals lambda minus 5, can only be solved if lambda equals 5. I can't have naught x equals 4. I can't have naught x equals 7. I can't have naught x equals minus 2. I can have naught x equals 0. Okay, so that final equation is only possible if lambda equals 5. Okay, so for consistency we must have lambda equals 5. If we've got lambda equals 5, then naught x equals 0 means that x can be absolutely anything we like. Let's suppose for the moment that we say that x is equal to alpha. Then the equation x plus y equals 2 tells me that y must be 2 minus x. In other words, y must be 2 minus alpha. And the equation x plus 2y plus z equals 5 tells me that z must be 5 minus x minus 2y. In other words, z must be 5 minus alpha, take away 2 lots of 2 minus alpha, which simplifies to being z equals 1 plus alpha. The marking on this question, well, the 3 marks for reducing the equations to echelon form, followed by a mark for pointing out that lambda had to equal 5 for consistency, and then there were 3 marks for solving the system of equations in the case when lambda equaled 5.